Right then, let's talk about vectors. A vector is a quantity that has both size and direction.
Imagine describing a bicycle's movement. You've mentioned speed and direction, like 10 kilometers per hour north. That's where vectors come in. They represent quantities with both magnitude and direction.
Vectors are absolutely crucial in physics and engineering. They're like the bread and butter of these fields. Why, you ask? Well, because so many physical quantities are best described using both magnitude and direction. Take forces, for example. When you push or pull an object, the force you apply has both a strength and a direction. It's the same with velocity, which tells us not just how fast an object is moving, but also where it's headed. Acceleration, too, is a vector quantity, describing how an object's velocity changes over time.
In engineering, vectors are essential for designing bridges, buildings, and all sorts of structures. Engineers use vectors to calculate the forces acting on different parts of a structure to ensure it can withstand the loads it's designed to carry. They also use vectors to model and analyze the flow of fluids, the behavior of electromagnetic fields, and much more.
Now, let's talk about how we can visualize these vectors. As we mentioned earlier, arrows are a handy way to represent vectors visually. The length of the arrow corresponds to the magnitude of the vector, and the direction the arrow points in gives us the vector's direction.
Imagine you're drawing a map of a treasure hunt, and the instructions say, walk 10 paces east, then 5 paces north. You could represent each leg of this journey with an arrow. The first arrow would be 10 units long and point east, while the second arrow would be 5 units long and point north.
We can also use diagrams to visualize the addition and subtraction of vectors. For example, if we want to add 2 vectors, we can draw the arrows representing those vectors tail to head. The arrow drawn from the tail of the first vector to the head of the second vector represents the sum of the 2 original vectors.
Section 4. Adding vectors, combining forces and displacements. Now let's delve into the fascinating world of vector operations, starting with addition. Imagine you and a friend are pushing a heavy table across the room. You're pushing with a force of 50 newtons towards the east, and your friend is pushing with a force of 30 newtons towards the north. How do we find the combined force acting on the table? This is where vector addition comes in.
We can represent your force with an arrow pointing east, 50 units long, and your friend's force with an arrow pointing north, 30 units long. To find the resultant force, we draw these arrows tail to head.
The arrow drawn from the tail of your force arrow to the head of your friend's force arrow represents the combined force. This new arrow's length and direction give us the magnitude and direction of the total force acting on the table. This tail-to-head method visually shows how we combine forces or any vector quantities with direction. Section 5. Subtracting vectors, finding differences and changes.
When it comes to subtracting vectors, the process is quite similar to addition, but with a slight twist. Instead of drawing the vectors tail to head, we reverse the direction of the vector we are subtracting and then add it to the first vector. This way, we can find the difference or change between the 2 vectors.
By reversing the direction of the vector we want to subtract and then adding it to the original vector, we can effectively determine the resultant vector that represents the difference between them. This technique is essential for understanding changes in velocity, force, and other vector quantities. Section 6. Scaling vectors.
Scaling a vector involves multiplying it by a scalar, which is just a fancy term for a regular number. When you scale a vector, you change its magnitude, but not its direction. For example, if you have a vector representing a force of 10 newtons and you scale it by 2, the new vector represents a force of 20 newtons in the same direction.
This concept is particularly useful in physics and engineering, where we often need to adjust the magnitude of a vector without altering its direction. By understanding how to scale vectors, we can accurately model and predict the behavior of various physical systems.
And there you have it. We've explored the fundamental operations of vectors addition, subtraction, and scaling. By mastering these concepts, you can better understand and solve problems in physics, engineering, and many other fields. Thanks for joining us, and we hope you found this journey into the world of vectors enlightening.
Stay curious, keep learning, and until next time, take care.